Thanks. So I work at Jane Street on the OCaml language team, where we've been having fun playing with type systems. So in the keynote this morning, there was a slide describing various types of formal verification technology. And scoring at the very, very bottom, in last place for level of guarantee provided, was type systems. However, it was also at the very bottom for level of effort required. It was the lowest effort tool to do some verification, and it was establishing the weakest, least interesting properties. So the work that we've been doing extending OCaml is about trying to maintain that very low level of effort while establishing more interesting, more sophisticated properties. So there are a few reasons why type systems are so low effort to use. I think I've listed a couple here, but there are more. The biggest one is that it's the language that the programmer or the agent is writing. It's not a separate specification in a different syntax in a logical model. It's all the same code. Part of the code is the type annotation, and it's got the same binding structure, scoping rules. The annotations are matching the data flow of the program, and importantly, because it's so integrated, it evolves along with it. You don't find yourself with the new version of the program and the old version of the proof and trying to work out what changes you have to make to the proof to make it work with the new version of the code. And finally, there's a long, long history of minimizing the amount of annotation that people using type systems actually have to write. So techniques like bidirectional type propagation or local type inference, or just full Hindley-Miller style annotation to just mean that programmers don't have to write any details beyond the program source at all. And as well as minimizing the amount that they have to write, there's also a lot of work on making it predictable where they do have to write something. So programmers have a good understanding of what things they're going to need to write and where they're going to need to write them. So it's generally just a very low effort way to establish some basic properties about your program. Traditionally, that property is just kind of precondition and postcondition on values. It takes this sort of inputs, it produces that sort of outputs. This is the view of types as being just sets of values. It's, if I give the program the shape of things it is expecting, will it give me back the shape of things it promises? But that property about just the result of the program, that's not actually what's going on in a type system. Types aren't classifying values. You don't give the type system a value and ask, is this good? They classify terms, whole computations, whole programs. So since it's going to be looking at the whole program anyway, there's no reason that the type system can't tell us things about what goes on during the evaluation of the program. So some examples of that from the literature are recent work on algebraic effect systems, or earlier work on type and effect systems. So here in those sort of systems, the thing the type system says about the program is not just A produces a result type, the answer is A, but also this extra information delta, the friends we made along the way. We might have raised an exception or done some IO, or just the set of possible things other than the answer, which could have happened during the program. And these are like very easy to implement and use, and give you extra information that's not just predicates and values. Similarly, even type systems as old as the simply type lambda calculus can tell us liveness properties as well as safety properties. They tell you that the programs terminate. Or there's been other work on information flow, separating high and low security terms and checking, confidentiality types, or checking that information from a high security context doesn't end up in a low security context, so you don't leak secrets. Or integrity types, which tell you that information from a low security context, that's attacker controlled inputs, aren't being used to make high security decisions. You aren't branching directly on untrusted inputs to decide which way to go in some important context. So there's a particular class of these systems that I'm going to focus on here, and it's those ones which mess about with the variables in scope. So traditional type systems, you have this variable rule that says, if you've got a variable in scope and it has type A, then you can use that variable and it will have type A. And there's quite a lot of scope for messing around with that. And it turns out you can express quite a lot of useful properties about programs in a really cheap to verify way by just messing around with the variable rule. So some examples of this are linear type systems that say, well, you have a thing of type A, but only once. Arrays variables, you have it, but only at compile time or only at macros, and it's not going to be present at runtime. Or Rust-style borrowing, of like, you have it, but only for now. And generally, there's just a lot of stuff can be usefully expressed just by restrictions on how you access variables. So at Jane Street, in our extended version of the OCaml programming language, we've done a bunch of work along these lines using a particular flavor of this called modal types, which I'm going to talk about a bit more. So OxCaml, the project that we work on, is a fast-moving set of extensions to the OCaml programming language. So like OCaml, it's an open source project. We have, it's all on GitHub at OxCaml/OxCaml. It's fast moving. We make much fewer stability guarantees. We break our own code every couple of weeks, and we'll probably break yours too if you try using it. I encourage you to do so, but accept that like it's a moving target. We've added various features that we're slowly trying to upstream into OCaml proper. So I think some of the smaller ones at the end, the polymorphic parameters and label tuples and so on, are in either the most recent, so some of those are in the most recent released version of OCaml, and some of them are in the version that's about to be released. But some of the more bigger changes, the modal types that I'm going to be talking about today, have not like made it into mainstream OCaml, and probably won't for a while because they're quite large changes. But despite the experimental nature of a lot of this, this is the language that Jane Street uses for all of our code, which is, I don't know, it's a 70 million line of code monorepo at this stage, although every time someone gives one of these talks, you have to update what that number is because it is growing quite quickly. And that all goes through the OxCaml compiler. So this is what we're using in production. So to describe what's going on with these modal types and how they work and what they're for, I'm going to start with an example. And it's not an interesting example. This is some code that would have worked in OCaml in 1992. There's a type, it's got an immutable field, it's representing a node of a graph, it's got one immutable field called its name, and it's got a mutable field for its successors, and it's got some accessor functions for making one of them, reading fields, writing fields, and so on. And in OCaml, you can write an implementation like this, and you can also write a signatures that is usable from other modules. And the signature represents the API of this module, and it's fairly straightforward. There's a type, you can make them, and you've got a couple of accessors. You can read them and iterate over them and do stuff with them. So here, the getName accesses the immutable field, and then addEdge and iterEdges access the mutable parts. So an example of using this module is here. I'm not going to, no particular need to like read the code in detail. It's just iterating over the nodes of this graph and printing them. But there's an interesting, if very small, verification problem here. It iterates over them by calling this iter function and passing a callback. So the convention in OCaml is to use what some languages call internal iteration. So this is, rather than an iterator type that you might have in, say, C++ or something, where the user writes their own for loop and asks your library for an iterator, the usual way of doing this in OCaml, and I think in most functional languages, is for libraries to provide an iterate function that accepts a callback. So you call the iterate function and you give it your loop body and it runs it on each element. So here's something where we open a file, iterate over nodes of this graph, print them all out, and then close the file. And the verification problem is, how do we know that the file is actually still open at the time that we start printing stuff to it? So OCaml is a memory-safe language, so the consequences of it being closed are an exception and a sad message printed to the screen, rather than a like C-style used after free that immediately becomes a remotely executable vulnerability for some reason. But still, it's something we'd rather not happen. We'd rather know that the file was actually still open at the time we started to use it. But that's not completely obvious. We know from writing the code that that iter_edges function is just going to call the callback. It's just going to loop over them, and it's just going to call it. But that's not obvious from its type. It could, in principle, take that callback, squirrel it away somewhere in some global data structure, and then 3 days later invoke it, by which time the file is long closed and you get the exception. So we'd really like to be able to verify that that doesn't happen, that this function is only going to be called at a time when it's actually still in use. And in the OxCaml version of OCaml, we can put a couple of extra annotations here. There are these @local modes. So the function for opening a file says the new channel that it's opening is @local, and the callback that it is given the file is also @local. But crucially, this iter_edges function says that it takes the closure that the callback that it's going to use is also taken locally. So that @local on a function, so that @local should be thought of as part of the arrow. So it's saying, this isn't just a function, this is a function that promises not to capture its argument. So it can use the argument, it can call it if it's a function, it can access its fields or whatever, but it can't survive any longer than the function call. So this was originally added to support stack allocations, that we can do a very efficient reuse of memory and know that it is safe to do so. But it's very useful for things like this API, where we're doing something and need to know that there's no more remaining references to the file handle before we close it. So the interesting thing is that we've only changed the description of the interface. I haven't actually changed the implementation. There's been no actual new code to support this. So this is in contrast to some more for instance, the big example is Rust lifetimes, which are very expressive but also fairly heavyweight. You have to do some work to write down the lifetime variables and explain to the compiler exactly how each of these things is being propagated. Whereas here, I put one annotation on the interface because if I wanted to use it from a different module, if this was all in one file, there wouldn't have to be any annotations at all. This is all completely inferred. And getting this level of inference to work, getting this level of really low annotation, is super important for a functional language like OCaml, where closures and higher order functions and lambdas you can have like several of them on every line of code. It's really, really important to have very lightweight ways to pass around functions like this. So I'm going to explain a bit about how that actually works, because it's a really useful bit of type system tech for anyone who's into building type systems. But unfortunately, I'm going to have to put horizontal lines and Greek letters on the screen in order to do so. So this is the standard typing rules for functions and variables. So the bottom one is the variable rule. The stuff to the left of the turnstile is all the stuff that's in scope, and it says if there's a thing of type A in scope, then use of the variable x as type A. And the top one says you can type check a function, the thing below, the fun x arrow e, by putting the variable in scope and then type checking the e. And I've left some strategic gaps here so that I can scribble all over them. So the modal type system is you scribble all over everything in the context and the outputs. So this is quite a lot. There's 3 different modes going on with that thing at the top. There's I, J, and K. I is describing the function that you're making. It's the output of the thing. J is describing the mode of the function's input, and K is describing the mode of the function's output. And then, so the context gets this lock symbol, telling you it was locked with a lock of type I. And then when you're trying to use a variable that was in scope from before that lock later on in the variable rule, it needs to be compatible with that lock. So what that ends up meaning is if I'm going to make a closure, so if I'm going to make a function, and that function isn't itself known to be local, if that function might escape or might be stored in some global variable or might be used beyond its scope, then that function can't access any variables that are local. So this is the thing that allows functions that pass to iter, so which are only ever going to be used locally, those can use those can use local things, but functions that might escape more widely can't. So this is like, that is a fairly simple thing to express, that a function that might leak can't use anything that's not allowed to leak, and this is not the simplest way to express it. This has a bunch of variables and less than symbols and more maths than should be necessary for a simple concept. But the reason it's expressed like this is this doesn't use the word local anywhere. This is completely generic in what type of property we're trying to express or capture. And in the actual implementation, those I, j, and k's are just variables, inference variables that the type system is able to work out on the fly according to the constraints of the rest of the program. So this expression where everything is just a variable is what lets us implement these type system features with extremely low developer effort. No one has to actually necessarily, like they can write annotations, but they don't have to. Okay, so that this system works for more than just checking that things don't escape a scope. The main reason that we built it or the main thing that we're using it for now is to verify data race freedoms, that we can use programs that use multiple threads and don't have to worry about mutable state being read and written from multiple threads at the same time. So to express this, we've added a bunch more modes. We're describing some values are marked as being portable. Portable means it can in the future be passed to other threads. It's a thing that is safe to share. And contended is something that has been passed to other threads, so you can no longer rely on having exclusive access to it. So mutable state can only be written when it's uncontended, but is by default completely portable. So this is a little different if you from most systems. It's actually completely fine in this system to pass values, even ones containing mutable state, to other threads. They can't just be shared. It's just only one thread will have them will have uncontended access to them at a time. So to handle read-only sharing of things, there's a point in between uncontended and contended where things are shared, and that describes values which might be read by multiple threads simultaneously, but definitely won't be written. So shared and uncontended work like Rust's alias store mutable, if you're familiar with that. It's uncontended means I am writing to it. I can read it or write it, and no one else can. Shared means I can read it but not write it, but maybe other people might be able to read it but not write it at the same time. But as well as those two, we have this additional one of contended values, which no one can read, which you just can't read and write, except for the immutable parts. So that means that with a bit more scribbling all over the interface, we can express. We can allow this library to be used in a multi-threaded context completely safely. In particular, we can read the name, access the immutable parts of a data structure without worrying which other threads are accessing it at the same time. So in particular, the getName function, it's okay to read the name of a node even if other threads are simultaneously reading and writing its mutable fields, because we know that that name field is an immutable one, so it can't possibly be ever changed, so it's perfectly safe to read and write, even if there are things happening in parallel without any locks. So getting that to work requires slightly more scribbling, which I won't explain in great detail, but I'll mention that still none of this refers to any of the particular modes, so it all still works for inference, and it all still requires no particular annotation by the programmer, no particular extra effort. So that's enough to get a classic nested parallel type programs, where there's a program that splits in two and does part of the work over here and part of the work over here, and we verify that the two parts of the work don't interfere and then collect the results afterwards. But interesting programs do actually have some shared state that they want to protect by a mutex or a lock or something. And those fit quite neatly into this modal model as well. So we've introduced this idea of capsules, which are an isolated graph containing arbitrary internal aliasing. So this is it's within a capsule. There can be cyclic references, there can be loops, there can be graphs, there can be pointers going any which way. There can be sharing, there can be whatever you like. But each individual capsule is isolated from all of the others. Mutable data can pass in and out of the capsule, but it becomes contented as soon as it leaves the capsule, so no one can read or write the contented parts of it. And that's enough to get a type interface to mutexes and locks and reader-writer mutexes and all of the standard concurrency data structures. We've got versions of them that are typed using this sort of stuff. So I won't explain in great detail what all of the annotations here are doing, but it's more that without the user having to write a lot of like lifetime annotations or complicated types, they can use these data structures safely. So the implementer of those data structures does have to know what all of those words mean. If you are writing a mutex library for other people to use, then you're going to have to understand what contented and portable mean. But any actual uses of these are all completely inferred by the type system. Some work in progress is to be able to abstract over some of these. So we occasionally end up having multiple versions of something which are all fairly similar. But generally, if you want to understand more about this type system, there's 2 published papers. One on focusing on memory management with collaboration with Anton Lorenzen, who did an internship at Jane Street for part of this work, but is now doing a PhD with Sam Lindley in Edinburgh. And a second paper at Popple last year on the database freedom and concurrency aspects of this, which was in collaboration with some people at MPI SWS, including Aina Benjamin and Leila, although Aina has recently moved to Jane Street and is working on mode polymorphism and modes checking. It's all open source on GitHub, and the documentation is all on oxcaml.org, and I'm happy to take questions.
Yeah, we have time for a question or two. Anyone has any? Sophia.
Thank you very much. I have read some of your older papers, and I found this introduction extremely enticing. On the other hand, I'm trying to place the work. There is a lot of work on, for instance, ownership types, isolation, immutable types, recently capturing types. Do you think that yours is a better space in the design, a better point in the design space? Or are you saying that by making these, I don't remember what you call those annotations, IJ and so on, parametric, you can have a system to rule them all? You can express all these systems?
So I think that it's definitely a different point in the design space. The trade-off we're going for is mostly lower programmer effort and accepting in some cases less expressivity for that. So we can't express everything that some prior systems can express, but because it's all parametric in these modes, we can do it with a lot less programmer annotation.
Great, thank you. Time for one more. I think Dominic had his hand up.
Okay. Yeah, thanks for a great talk. So I agree that the annotations are quite lightweight on the types, and that maybe the implementer of the library is the only one who needs to know what the terms mean. But what about for errors? When inference says this is not typable, doesn't the programmer need to understand why it's not typable?
Right. Yes. Generating good error messages for this system is always kind of a challenge. So one advantage here is that the programmer only has to understand the errors in a specific concrete context where they know what they're doing. So that's usually easier to explain than like the general constraints of everything that is possible with the system. The other point there is that having a customizable, like a user specified amount of annotation does make that process a little bit nicer, because you get an error, you can add some extra annotations that you think are true halfway through and see which direction that moves the error, and like kind of refine your understanding that way. But it's still like not great. There's definitely work to be done there.
Thanks.